Hi, so this is Maharshi Ray, and I'm going to talk about graph-theoretic approaches to dimension witnessing. And this is a recent joint work with Naresh Kishore Quek and Adan Cabello. So we are going to talk about dimension witnessing, the Cabello-Severani-Winter framework, which is crucial for our work. And then we are going to introduce dimension witnessing in contextuality scenarios. And we are going to describe our main result, which is an explicit construction of a family of graphs, which can help us to construct dimension witnesses for arbitrary high dimensions. And we will conclude with some open problems. So here is the main idea behind quantum dimension witnesses. So while it has been studied in many scenarios, I'm going to describe only a non-local scenario here. So imagine Alice and Bob being asked some questions X and Y from some set of questions, and they are giving some outputs A and B. And suppose in the quantum world, they are sharing some quantum state between them. So people study the correlations that are generated by such experiments in terms of this conditional probabilities, probability of AB given X and Y. So in particular, the Bell inequalities are just like a linear combinations of these correlations. And so in the dimension witnesses, you put an additional restrictions on the dimensions of these quantum systems. Here, you are restricting it to size D, and we are denoting the corresponding set of correlations that can be generated as this PD. And this the maximum quantum value that can be achieved with this D dimensional quantum systems is given by this SDQ. Now, suppose you run this experiment and get a value which is greater than this, then it means that the underlying quantum system has dimension at least greater than or equal to D plus 1. So this simple idea has been explored in several scenarios, and one can find the references here. In this work, we concentrate mostly on the contextual framework, and for that, we must introduce this CSW framework. So imagine you have this n measurement events, E1 to En, and two events, we call them exclusive if they cannot happen together. And for them, we construct this graph called the exclusivity graph, having n vertices, and we draw an edge between them, edge between I and j, if events ei and ej are exclusive. Next, we assign some like real values between 0 and 1 to each of the vertices of this graph. So we denote this by this vector p of n dimensions, and which we also call as a behavior. And we have this rule that pi plus pj must be at max 1 for every edge I and j. Okay, so now depending upon different theories, you put additional rules to these assignments. And so, for example, in the deterministic non-contextual theories, you are only allowed to assign like binary values, 0 or 1, to the vertices. So one can now easily see that for behaviors corresponding to this deterministic non-contextual theories, they are nothing but the characteristic vectors of the stable set of this graph. Just to recall, the stable sets are like a subset of the vertices such that no two of them share an edge between them. So if you take a convex hull of these deterministic non-contextual behaviors, you end up with what is known as a non-contextual set. So it was shown in the CSW14 paper that this polytope of non-contextual behavior is the stab of the graph. Now, when we move on to the quantum world, for this exclusivity graph GX, we say that the behavior is quantum if there exists the state psi and the projectors pi1 to pi n, such that you can write pi as this inner product psi pi I psi, and the trace of pi I pi j is equal to 0 for every edge I between I and j. So here the pi I to pi n, which satisfies this second condition, is also known as a orthonormal representation of this graph. So just like the classical set was characterized by this tab of this graph, the quantum set turns out to be can be characterized by this set called the theta body. So that was another result of the CSW paper, that the quantum set is given by this theta body. And this theta body is a combinatorial object. It is defined by this following way. So we have this theta body is like a vector which belongs to theta body. If there exists a positive semi-definite matrix X of size n+1, such that you have this X in the diagonal of this capital X matrix, and we at the top left entry is 1, and then the top row of the X matrix is equal to the diagonal of the X, and then whenever there's an edge between I and J of the graph, you have to put the corresponding Xij entry to be 0. So the bottom line is that to test whether this X is in the theta bodies or not, you can just solve an STP for it. Okay, so we look at some graph invariants here. So independence number is the largest, is the size of the largest stable set, and it's denoted by alpha. Then we have this lowest theta number, where we saw that this feasible set is the theta body, and you are trying to maximize the sum of the diagonal terms. Then we have this chromatic number, which is the minimum number of colors that you need to have to color a graph, such that no two adjacent vertices share an edge. No two adjacent vertices have the same color, and it's denoted by the sky. And the sandwich theorem tells you that this alpha of G and this chromatic number, so they are like NP hard to compute. Although they are NP hard to compute, they can be, there is this lowest theta which can sit in between these two quantities. And this is known as a sandwich theorem, and it's quite interesting. Okay, so the next we come to this non-contextuality inequalities. So we have that these facets of this non-contextual polytope is given by these non-contextuality inequalities, and they are of this form that you take a weighted sum of these components of these behaviors in the classical this non-contextual set, and they are upper bounded by this weighted independence number. On the other hand, if you take the quantum value of this expression, that is, you take P to be in the theta body, then the maximum value that you can achieve is given by the weighted lowest theta number. So this KCBS inequalities are like the most simplest of these non-contextuality inequalities, corresponding to the graph where the graph which is a pentagon. Okay, so here in the pentagon case, you have the independence number equal to 2, whereas the lowest theta number there is equal to square root of 5. So here we see a classical quantum gap here. Okay, so now we put like some dimensional restrictions on this quantum correlations. So now we call a behavior to be d quantum if there exists a d dimensional quantum state and projectors phi1 to pi n, such that you can write this pi as this inner product, and this trace of pi I pi j is equal to 0 for every edge as before. And we call this pi1 to pi n as a d-dimensional orthonormal representation of the graph. We define an orthogonal rank which is R0 of this graph as the minimum d, such that there exists a d-dimensional orthonormal representation of this graph. Then we put restrictions on this lowest theta STP. So we have the same set of constraints, except that we put an additional rank constraint here. Rank of X is at most D. And we call this program a restricted lowest theta program of dimension D. Then we have this lowest rank, which is defined as denoted by RL, and it is the minimum D for which the lowest theta is equal to the rank restricted lowest theta for rank D. Okay, so from the previous slide, it should be clear that as we increase the rank, allowed rank of this program, the feasibility set grows, and therefore the objective value should grow. And that is captured by this following set of sequence of qualities. And this gives us a way to kind of figure out dimension witness in particular. So if we consider inequality of this form, that summation of pi, where p is from this quantum set, is at most is the theta lowest theta restricted to D, then suppose you violate this inequality, then it implies that the underlying quantum systems must have dimension greater than or equal to D plus 1. So what we show here is that we identify a class of graphs which allows us to certify arbitrary high quantum dimensions. So our family of graphs is what we call a kite graph, and it consists of k-kite graph has 2k plus 1 vertices, and I'll explain the construction using an example. So it consists of 3 layers. So in the first step, we have a k complete graph. So in this case, we have k equal to 3. So we have 1, 2, and 3. In the next step, we add a node for each of the nodes in the first layer. So we have 4, 5, and 6. And in the third step, we add another extra node, which is 7, and join it to all the nodes in the second layer. So 7 connected to 6, 4, and 5. And one can note that for k equal to 2, this turns out to be pentagon. And one can also extend the same construction for every k. So what we know for the results that we derive for this family are as follows. So we show that the independence number for this graph is, for the k-kite graph is k, which is kind of simple to show. Then we show that there exists a orthonormal representation of this graph of k-kite in dimension k. Then there's this fact that the lowest theta number for this graph for k-kite is greater than k by running an STP. And the main theorem is that when we look at this rank restricted lowest theta for these class of graphs, we showed that the k restricted lowest theta number is at max k. So this gives a separation, and we use that to arrive at our main result, which is that we look at this contextuality, non-contextuality inequality given by this. So you take P to be in the quantum set, and summation of Pi is at max this k. And suppose you violate this inequality, then it implies that the underlying quantum realization must have dimension at least k plus 1. So to conclude, we kind of give you a procedure to certify dimension of local quantum system of arbitrary high dimensions. And we leave here with some open problems. And thank you for your attention.